Okay, I hope the first part of the homework went well for you. Now let's look at the next few problems on the homework. So if you're going to discuss continuity just overall on graphs, you're either going to say something like the graph or like P of X is continuous on its whole domain, or you're going to say P of X is discontinuous at, and you'll name specific X values. So in order to make comments like that, what you're going to want to do is draw quick graphs as quick as you can. Well, I see that P of X is a cubic function, and I see that its leading coefficient, 3, is positive. So I know in general cubic functions look like this. And if their leading coefficient is positive, I know that they rise on the right-hand end. Well, basic polynomial functions like this don't have poles, i.e. vertical asymptotes, and they don't have jump discontinuities. So P of X is continuous on its entire domain. So I could say for all real numbers, or I could say on negative infinity to positive infinity. So FYI, guys, all polynomial functions are always continuous. And so those are really nice functions to use for certain examples that we'll get to later, especially later in this lesson that deal with the intermediate value theorem. All right, so with rational functions, you all know that rational functions tend to come in pieces. And so the biggest thing you're looking for would be vertical asymptotes. Well, if I'm going to think about the way this is graphed, you know my first job is to factor it. Oh, so here's what I know off the bat. The domain of R of X is all X such that X does not equal plus or minus 2. Because those are the X values that make the denominator 0. And you all know that any X value that's not in the domain is either going to be a vertical asymptote on the graph or a hole in the graph. So of course, I know that the X plus 2's cancel, so that R of X becomes 1 over X minus 2 with a hole at X equals negative 2, since it was X plus 2 that canceled out. So guys, I know that R of X is discontinuous at both X equals plus or minus 2. But let me say this sort of completely, but I'm still being a little bit informal because I'm not actually proving it or justifying with the formal notation. But I'm going to say R of X is discontinuous at X equals 2, and I'm going to put in parentheses the reason is that you've got a vertical asymptote at X equals 2, and at X equals negative 2, and I'm going to say that's because that's where the hole in the graph is. So I'm mentioning why the discontinuities are there, but I'm only being informal when I mention it. I'm not actually proving by doing the three-part conditional test. So for all rational functions, check for vertical asymptotes and for holes in the graph, and that's where your discontinuities will occur. All right, so think about any y equals sine x graph or transformation of the graph. Are we clear that sine and cosine are both just these real uniform repetitive periodic waves? These waves never have holes in the graph, they never have vertical asymptotes, and they never have jump discontinuities. So guys, it does not matter that this pi over 4 is creating a period change, you know, a horizontal stretch or shrink. That doesn't matter at all. The graph is still that basic wave. So just like polynomial functions, any sine and cosine wave is always going to be continuous over its whole domain. So I didn't say that, but I could say that h of x is continuous. And again, I could say for all real numbers, or I could say from on negative to infinity to positive infinity, since I said for all real numbers last time. I'm just kind of mixing up the way I'm saying it, so you'll get used to several different opportunities for how you write things. All right, so is tangent x like sine and cosine? Well, no. You all know that when I graph tangent x and cotangent x, you know that I get the graphs. So if I say pi over 2, pi, 3 pi over 2, 2 pi. So we know, remember, that tangent x is sine x over cosine x. Tangent x is 0 when sine x equals 0, which is on the 0 and all the pi's. Tangent x is undefined when cosine x equals 0, and where it's undefined, it has vertical asymptotes. And so you know I'm going to be getting this kind of graph. And you know the same kind of thing is true for y equals cotangent x. So those two graphs have lots of discontinuities. So the domain would be all x, such that x does not equal plus or minus pi over 2, plus or minus 3 pi over 2. I'm saying this more formally now, right? 5 pi over 2 and a dot, 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 dot. So that means k of x is discontinuous at x equals all of those pi over 2. So now I'm going to be a little bit informal since I've already listed it formal once. And remember, why is it discontinuous? Well, informally, because of vertical asymptotes. Formally, I would need again to go back and say something like k of pi over 2 does not exist, so k of x cannot be continuous at x equals pi over 2, etc., etc. So guys, for the other 4 trig functions, all of them have vertical asymptotes. So those vertical asymptotes are where your points of discontinuity occur. All right, last but not least, what you'll be asked about frequently, piecewise functions. So I'm going to sketch my piecewise functions. Let me remind you that I like to look, for instance, at m of x and go, okay, the first piece is a right side up. I think I'll write with a pen. I usually have more luck when I do. The first piece is a right side up parabola. The second piece is a line with a positive slope. Things seem to be changing at x equals -2. If I plug -2 into my first piece, I would have to wind up with an open circle since its x is less than -2, not less than or equal to. And so -2 squared is 4. 4 plus 5 is 9. And then the second piece would start at x equals -2. It looks like -3. So now when I graph it, let's see here, -2, 9. Oh, no. Let me make that an open circle. Now, the graph, actually, if you think about it, is 1, 2, 3, 4, 5. The graph is a parabola that looks like this, right? That's what y equals x squared plus 5 looks like, but I can only have the parabola to the left-hand side, so I'm going to actually wind up erasing the part of the graph that looks like the parabola. So all this stuff goes. I was trying to just do the whole graph in order to try to achieve some sort of shape that looks right. Having issues again with it not graphing where I mean for it to. So I've got those a little squashed together, sorry. All right, so the other piece of the graph at x equals -2, -3 starts with a closed circle, and the slope is 1, so up 1, right 1. And then I'm just going to do that. So I've got my graph. I see that there's a huge jump discontinuity at x equals -2, excuse me. So what I've got to do at this point is I want to actually say formally, why is that? So does it look like the problem is that m of negative 2 does not exist? No, because m of negative 2 does exist, and it's equal to negative 3 down here at that closed-in point. Does it look like the limit as x goes to negative 2 of m of x does not exist? That's your reason. So I'm going to say formally the limit as x goes to negative 2 from the left of m of x is equal to, it looks like 9, and that's not equal to negative 3, which is the limit as x goes to negative 2 from the right of m of x. What's that mean? So I'm going to say, therefore, let me get rid of the extra little dots that just showed up. I didn't actually touch the board there. So therefore, and I'm going to use my mathematical symbols to make it quicker. Therefore, the limit as x goes to negative 2 of m of x does not exist, which in turn makes m of x discontinuous at x equals negative 2. So the limit of m of x does not exist, and m of x is discontinuous at x equals negative 2. Now I've gotten the formal lingo in there. So I proved that the limit does not exist because the left-hand and right-hand limits don't exist. And I proved that the function is discontinuous at x equals negative 2 because the limit does not exist. So I'm building using all these things that I've learned. Notice, guys, that when you found the hole in the graph at negative 2, 9, what you were finding was your left-hand limit. And when you found the closed circle at negative 2, negative 3, what you were finding was the right-hand limit. So even though I kind of used those little notes to myself to figure out how to graph the function, I'm actually also doing the left and right-hand limits, which helps me when it comes to the calculus part of it. All right. Now, notice, by the way, I didn't say this. I sort of inferred it, but I should have been specific. When I look at the parabola and the line, both of those are polynomial functions, and the two pieces of the graph then are continuous. What you're really looking for is what happens at the x values of change, where you change from one piece to another piece of the graph. So I could also say the right-hand piece is continuous at x equals negative 2 from the right, but the left-hand piece is discontinuous at x equals negative 2 coming from the left, because you have a hole on the left piece, but everything's fine on the right-hand piece. So now you know how this is going to roll. So let's do something similar with number 6. So I know that y equals 5 is just a horizontal line. And I know that the horizontal line at 1, 5 is closed there, and that horizontal line runs leftward. So that's done. I like that part. That was easy. So then at the second piece, 3x plus 2 is a diagonal line. So both of the lines are continuous. The question is, do the two lines connect, or are they disconnected with a jump discontinuity? So on this piece, I'm going to say, well, there's an open circle at 1, 5. Yay! So this piece starts at 1, 5, so its open circle there connects to the closed circle, so you can't see it. They connect to each other. And I know I'm going to go up 3, right 1 from there. If I want to be really good with my slopes, I can be. So even though this creates a broken line, the line is not discontinuous. So that's pretty cool. So I'm just going to be able to say n of x is everywhere continuous, or it's continuous for all real numbers, or it's continuous over its entire domain. So on this one, the two individual pieces were already continuous. I checked to see what was happening at the x value of change, and since the two pieces connected to each other, we're good. So if you want me to also say something there to be more specific, I could say n of x is continuous specifically at the x value of change, so at x equals 1, because, go back to the three-part test, what is n of 1? Well, n of 1 was 5. And that is equal to the limit as x goes to 1 of n of x. So I keep coming back to that one basic definition. So in essence, whenever you're doing piecewise functions, look at the individual pieces. Assure yourself that the individual pieces don't have holes, poles, or jumps. And then quickly check what's going on at the x values where you change from one piece of the function to the next piece of the function. All right, so let's do some more homework.